Our entertainment is electronic, our gadgets are electronic, our communications are electronic, lighting electronic, our soapboxes and forums electronic. Everything here was made using electricity. But could you explain electricity to a friend or a child? Electricity is essentially the movement of charge, usually in the form of electrons. And to demonstrate this, I have a basic circuit with a couple of wires and a motor. Now, all the wires and components of the motor are made of metals, which have something called delocalized electrons, which means they're free to move around if given the energy to do so. So if we supply some energy by using this battery, the motor begins to work. And if we disconnect the battery, the motor cuts out. There are three key words used when talking about circuits like this: voltage, current, and resistance. Resistance is simplest. It's how much resistance the electrons find when they try and move around the circuit. Current is the amount of charge passing through a given point, so essentially the number of electrons. Voltage is the amount of energy that each electron has. In UK schools, voltage is commonly talked about as the electrons carrying small packets of energy with them from the battery to a component in the circuit. Well, initially this would make sense in a direct current circuit, like this one. Direct current just means that the electrons flow in one direction the whole way through. But if you have AC, alternating current, like in the mains power if you use a socket plug, then the electrons don't actually make circuits. They just shudder backwards and forwards over again in the same spot. And if they're carrying packets of energy with them, and they're just going past the same spot, how do they give this energy to the components? So to find out what the energy in a circuit really is, we have to start talking about something a bit more advanced. The electric charge carriers are monopoles, which means they're entirely positive or entirely negative, and they create an electric field around them. And by convention, we draw the field from the positive to the negative. Of course, if we had two charges this close to each other, their fields would be interacting. So let's fix that now. And now it shows the two charges being attracted together. Now if you put together all the billions of electrons in a circuit, as you can imagine, the field gets quite complicated. But we can make it easier by taking a macroscopic view of the whole field and seeing how it behaves. I'll use a gravitational analogy to try and explain how the electric field works in terms you might have seen before. If we have a paper track and a steel ball bearing, and we place this ball bearing on the track flat, the ball bearing does not move. This is because the ball bearing is at its local minimum in gravitational potential. However, if we raise the sliders on and increase its potential above the minimum, it flows down towards the minimum. Now, if you imagine this as an electron, and this as the electric field around the circuit, when there is no battery connected, the field is uniform and the electron does not flow. However, by adding a battery, we cause a potential difference to form, and like before, the electron now flows. And as that electron passes along the field, it turns its electric potential energy into other forms, such as heat. When it reaches the bottom of the potential well, the battery's reaction recycles it into a new high potential electron. Now, we can make lots of different special materials in order to get different forms of energy out of this, other than just the usual heat. For instance, how does an electric motor work? It works off the curious principle that if you make an electron move through space, you turn it into a magnet. This may sound quite strange, and you're wondering why this is, and it's because of the dual nature of electromagnetism. So subscribe for more science and to find out how magnets work next week.